In this chapter, we are going to talk about aldehydes and ketones. Aldehydes are shown here in yellow, and they show up in things like formaldehyde, which is used to preserve specimens, as well as some flavoring agents like benzaldehyde, which is found in cherry flavoring. Then we also have ketones, which have a C double bond O right here. Those are found in some biological molecules like pyruvate, which is shown here. This is butadiene. The di just stands for 2, and you can see there's 2 ketones here. And this is in artificial butter flavoring. So these are a few places that these functional groups show up. So let's review the carbonyl group just really quickly. The carbonyl group is just a carbon that is double bonded to an oxygen atom and single bonded to 2 other atoms. Now, in this particular screencast and chapter, we are going to look at aldehydes and ketones. In aldehydes, these have that carbonyl group, and they have at least 1 hydrogen attached to the carbonyl, and ketones have 2 carbons attached to the carbonyl. By default, this means that as far as aldehydes are concerned, they'll either come at the beginning or end of the molecule, and then ketones will always be somewhere in the middle of the molecule, so they'll never be at the beginning or the end. And let's look at what I mean by this. Aldehydes and ketones occur widely in nature, and they're going to play really important roles in living organisms. And so, for example, we find these functional groups in things like glucose and fructose. Glucose is the major source of energy in living systems. And then we find fructose, for example, is found in things like cane sugar. Now, when we look at this, notice we've got an aldehyde functional group right here. We've got the carbonyl group, and then it's bonded to a hydrogen. It's only going to be at the beginning or end of the molecule, because if we look at this carbonyl group here in the middle of the molecule on fructose, that means that it's going to be by default in between 2 carbons. So that's a really nice way to be able to identify if something is an aldehyde or a ketone. Now, in this chapter, we're going to study the naming of aldehydes and ketones, and that's what we're going to do in this screencast. And then in the next screencast, we're going to look at some of their important reactions. But these concepts in particular are going to be really useful when we look at carbohydrates in chapter 17. So I just wanted to kind of point out where we're going to build on this information. Now, here are some common aldehydes and ketones in addition to formaldehyde. What you're going to notice is they have a common name as well as an IUPAC name here. The IUPAC name specifically, we see this AL for aldehydes. And so that lets us know that it's an aldehyde. There's one exception to this, and that's benzaldehyde here, which is the benzene ring with an aldehyde off of it. Then we can come down here and see ketones, and again we're going to see there's some common names like acetone, which is commonly found in fingernail polish remover, and then IUPAC names like propanone, for example, which ends in the ONE ending, and that lets us know, hey, look, that's a ketone. So it's really nice because we've got the AL of aldehydes and the AL here. And then the ketones, we've got the ONE of the ketone here, and it matches the ONE here. So really nice to be able to kind of recognize those endings. Now, what we're going to do is talk more about this IUPAC name nomenclature in the next slide. So when we're naming aldehydes, you need to select the longest chain that includes the carbonyl carbon, and then give it an alkane name, and then the E of the alkane name that has the same number of carbons is dropped and replaced with an AL. Here is the biggest deviation that I see from the normal rules, is that the carbonyl carbon is always going to be at the beginning or the end of the chain in aldehydes. So it's designated as carbon number 1. And because it's always designated like this, we don't have to put it in the name. We omit the number from the name. So let's do an example. If I were to, for example, look at this guy here, I would first off recognize that it's an aldehyde because we have the C double bond OH here. And then that carbonyl carbon of the aldehyde is automatically 1. And so that would be 2. And so this is a 2 carbon chain. And so what we would do is we would say that's great. That base name would be ethane, right, with the E there. And we're going to drop that E and add an AL, and this would be ethanol. Now, we do not put the number because it's understood that the carbonyl carbon there is the 1. Let's look at another one. Oh, and I've messed up. So let me come in here. I actually want to give that a functional group so that we can, not a functional group, a substituent, so that we can practice naming substituents as well. So when we look at this particular molecule, we see there's 1, 2, 3, 4 carbons. And so we would say, great, that has the prefix of butane. We drop the E and add the AL. We count from the carbon of the carbonyl, 1, 2, 3, 4. And so we're not going to put the 1 in there because it's understood. But we need to come over here and we need to say, all right, what position is this bromine in? And we can see that it's in the 3rd position. So this would be 3-bromo-butanol. And so we're going to let's do one more example. And this is what I would consider a trickier example, because you want to, the way it's written, read it like this and try to give this a position of 3. And so what you have to remember here is that you need to select the longest chain that includes the carbonyl carbon. And so this is going to be, by default, the 1 carbon here, and this will be the 2 carbon. And then no matter which way you count, right, it's a 4 carbon chain. And so that again gives us butanol. And then what we need to do here is we need to come in and we need to say, all right, this is then the substituent. There are 2 carbons as part of that substituent, and it's off the 2nd carbon of the chain. So it would be 2-ethyl butanol. No space there, I just left a space for writing, but that's what we would see as far as naming aldehydes. Let's talk about naming ketones. When we name ketones, we are going to choose the longest chain that includes the carbonyl group, right? And we give it the name of the alkane. Like with aldehydes, we drop the E and replace it with an ONE. The chain is numbered from the end closest to the carbonyl carbon, and we do give the carbonyl carbon a number, okay, because it can be multiple places. Now, there's an exception for this, and it's the smaller one, and so I want to show you the exception first. Okay, with this, there are 3 carbons there. This is called propanone with no number. And the reason it has no number is because there's only one place this carbonyl carbon that's a ketone can be. If it were on the first or third carbon, it would end up being an aldehyde. And so by default, this gets no number. But once we get into larger molecules, then we start to number. So let's look at an example of that. All right, so we are going to look and see that our longest carbon chain is here, 1, 2, 3, 4, 5. And so that would end up with the base name of pentane. We drop the E and add the O-N-E, so it's pentanone. And then we're going to number from the side closest to the carbonyl carbon. So 1, 2, 3. We could continue to go on, but we don't have any substituents there. And so we're going to put a 2 in front of the pentanone to tell us that's the location of the carbonyl carbon. And then we're going to tell the location of the methyl substituent that's located right here. And so it would be 3-methyl-2-pentanone. We haven't done any cyclic molecules, and I don't want us to forget about those. So let's come over here. And look at this molecule here. Now, when you have a cyclic molecule and there's only one carbonyl carbon, just like any other substituent, it's understood that that position there is the 1, and so we don't give it a number, but we would give a number to the methyl. So this would be cyclohexanone with no number because it's understood that double bond's in the 1 position. And then it would be 2-methyl cyclohexanone. So we'll do more of these examples in class. And as always, if you have any questions, please feel free to reach out. Now, the last couple slides, we are going to talk about some physical properties of the aldehydes and the ketones. And many of these physical properties can be explained by looking at their structure. Specifically, they lack a hydrogen on the oxygen, and so that prevents them from forming hydrogen bonds between molecules. So the lack of hydrogen on the oxygen of aldehydes and ketones prevents formation of hydrogen bonds. Right? So what that means then is that the boiling points of pure aldehydes and ketones are much lower than those of alcohols with similar molecular weights. So the boiling points of aldehyde and ketones is lower than alcohols of similar molecular weights. Because the aldehydes and ketones cannot form hydrogen bonds, and hydrogen bonds are going to increase the boiling point. Additionally, what we find is that the boiling point of aldehydes and ketones are higher than alkanes because the aldehydes and ketones have dipole interactions. Okay, and I've given you this in words, but I know some people think more graphically. And so if we look at this particular graph, which is boiling point versus molecular weight, and we compare kind of alcohols and aldehydes and ketones. Aldehydes here are in the white dot, ketones are the green dot, and then alkanes that are about the same molecular weight right in here. We can see that if their molecular weight's right around 60, that alkanes at room temperature are going to end up being gases, right? And then we can see that these would end up being liquids at room temperature. And we can also see that the boiling point here increases where primary alcohols have the highest boiling point, and then aldehydes and ketones are next, and then alkanes are the lowest. Now, I mentioned that these have dipole-dipole interactions, and the reason they have dipole-dipole interactions is because the difference in polarity between the carbon and the oxygen of the carbonyl group here. Oxygen is much more electronegative. And so what that means is it pulls electrons this way, and we're going to carry a partial negative charge, and then here this carbon will end up being partially positive. And this difference here results in dipole-dipole interactions between aldehydes, molecules of aldehydes that are the same, or ketones that are the same. Now, maybe the burning question in your heart is, Dr. Pierce, do aldehydes and ketones dissolve in water? And the answer to that would be if they have a low molecular weight. So what we see here is that the carbonyl oxygen exhibits dipole attractions Let's pretend like I spelled attractions right. Attractions. There we go. And forms hydrogen bonds with water. So while aldehydes and ketones can't hydrogen bond with themselves, they can form a hydrogen bond with water. And so because of this, that means that some aldehydes and ketones that particularly have low molecular weight are soluble in water. So I just want to, at the kind of end here, compare physical properties. And so if we look at an alkane, an aldehyde, a ketone, and an alcohol, and we look at molecules that have similar molecular weights. So we see here, we would be looking at butane, which has a molecular weight of 58, propanol, which has a molecular weight of 58, propanone, which has a molecular weight of 58, and then one propanol, which has a molecular weight of 60, I want you to notice that the boiling point increases as we go from alkane to kind of aldehyde and ketone are close together to alcohol. And the reason that we see, particularly for the boiling point, is that aldehydes and ketones have dipole interactions as well as London dispersion forces. And then alcohols not only have dipole interactions, but they also have hydrogen bonds, right? They also have London dispersion. And then these aldehydes and ketones also have London dispersion and dipole interactions, but alkanes just have those London dispersion forces. And so what we're seeing here is that as the intermolecular forces increase in strength, then the boiling point also increases in strength. And the reason that happens is because if you think about it, right, we have a liquid here and a gas here. And if you think about molecules, which I'm just going to represent with M here, if we have really strong interactions, it's going to be hard for one of these molecules to fling from the liquid state to the gas state. Okay, it's just going to be really hard because they're going to be held down here with all the other ones. So hydrogen bonds are really strong. They're going to hold on to these molecules in the liquid. London dispersion forces are really weak, and so it's a lot easier for those molecules of butane to escape into the gas phase, and that's why its boiling point is lower. It doesn't take as much energy to fling those molecules from the liquid phase into the gas phase. Alcohols, with their hydrogen bonds, those other molecules are hanging on to that molecule there really, really tightly. And so it takes a lot more energy to break these kind of these intermolecular force bonds here than it did for the alkane. So that's one way to look at it. So that's the trend that we see in boiling point. And if you need to go back and review your intermolecular forces, remember that I have a review screencast, and as always, you can come to my office and ask questions. And then what we can see is the difference in solubility for these low molecular weight alcohols and aldehydes and ketones is that we see that they're soluble here compared to the alkane, which is insoluble, because the aldehyde and the ketone, while they don't have hydrogen bonding within a pure sample of this molecule, once you put it in water, this carbonyl group can participate in hydrogen bonding. And so that's why we see that here. So once it's in water, we see that we can have hydrogen bonding in water, which results in that increased solubility. So, as always, if you have any questions, let me know, and we will work on this more in class.